that becomes a completely random observation in quantum mechanics. You make an observation, you make a measurement, the outcome of the measurement, you will get some eigenvalue, something random, not very specific. So quantum mechanical measurements are not specific, or it cannot be deterministic. It's kind of probabilistic. So you make one measurement 1,000 times, you will get different outcomes. And every time, as soon as you make the measurement, the state on which you make the measurement, the state will be changed. So you prepare a quantum system, you prepare a state, you prepare a very sophisticated operator to perform the measurement. Do one measurement, you get one random value. And you cannot reproduce the same result by doing the same experiment. You repeat the same experiment second times, starting from a very new initial state, you will get a completely different value. That is what makes quantum experiment very, very complicated and expensive. That is why quantum systems, so right now, after this, whatever we are now, the whole game of quantum computing or quantum hardware is developing a physical system which you can control. So you are making a physical system where you can think what state I want to prepare. Those are the states known as qubits that is used in the conventional quantum computing setup, and you may have heard that thousands of times. So a qubit is a specific quantum state. If you take superposition of qubits, that's a complicated quantum state, and there can be infinite possibilities for some states. As you have been hearing that you will have a system of 156 qubit quantum computer. So you can think of that as a huge physical system where you have access to independent 156 two-level systems in mind, and you need to engineer the controls so that any measurement or observation you want to make is to be achieved by those. Those are the quantum gates that you often hear popularly, like the CNOT gates, rotation gates, blah blah. Those are basically operators which acts on the quantum states and gives you certain outcomes. So this is the whole game of quantum hardware and controlling it. And the challenge, as you can already see, it's an extremely expensive, technologically advanced task, that how can you actually control a quantum system and make use of it. So right now, there are several technology giants who have succeeded to prepare such quantum systems in practice. This is a miracle that we now have quantum computers available with us. Now the next level of challenge is how can you use this as a technology solution. And this journey has begun, and you are all listening to this talk today, and we will be starting to work on this soon. So you are all definitely part of this. And in Amaravati, what we are going to have is a quantum bank which will house this IBM quantum system, and quantum hackathon that we will have in near future is a step or a staircase to enter into this bigger world. This is the world of future, and you are just stepping into it. So, as you can think of, what we are now deciding, it's a change of paradigm in terms of how computation works. We have all used classical computers, we all have a smartphone in our pocket now, and which is nothing but a computer. And that has evolved. Even when I was a child or of your age, I didn't have a computer in my pocket, but you have. So the technology has evolved so fast. So it's very interesting to look into the journey, how the classical computing evolved and how that has reached at a stage where we can just being able to from across the country or even beyond. So there has been several generations of computer hardware that has been evolved. If you can think of where are we now in terms of quantum computer, you maybe think of at most first generation or the boundary between first and second generation, where you might have seen classical computers of big room-sized systems. And right now, the IBM quantum computer that you will have, that's also a huge setup which will never fit in your pocket in a smartphone right now. So we are at the very early stage of hardware development when it comes to when it comes to a computer. But we have had a lot of lessons from classical computing era. So classical computing evolved. It started with the Turing machine in 1940s, 30s, and it evolved to the current stage of supercomputers. What has happened in between is there have been layers of improvements, and it's only until 1970s or so where people started realizing that computers are of actual use. And scientific computing started happening using those computers and more. So if you just look at the journey, it is 1948 where the first computer program was written on and it was run on a computer. So this analog of this in quantum era kind of happened maybe 5 or 6 years back, where an actual code was running on a computer. Then over time, the application development took place more and more that only as hardware also progresses. Yeah, as I mentioned, it's around 1970s where computers became a reality. PCs appeared, supercomputer even started to be made, and then there was a boom and that happened because this microprocessor technology was developed. That made computing scale down, the computer chip became smaller and smaller, and then this, right now, you have been hearing a lot of times that computing is available over cloud. So right now we are living in the era of cloud computing and supercomputing. Even National Supercomputing Mission is already been launched and has produced supercomputers within India. So we are now entering at this stage when it comes to classical computer. And then the question obvious is, why are classical computing useful for? The high performance computing, HPC is a word that you might have heard or you keep hearing. And you also hear certain aspects like data science. There are also fields which you may not be very familiar at this level, which are computational science. So, for example, data science is a interplay of domain knowledge where computer science will be used for engineering computer systems and statistical analysis of that, incorporating machine learning and all. This creates the field of data science where data can be used to advance the knowledge. Computer science or computational science is rather beyond data to understand computers for discoveries. So that has made huge progress over last maybe 2-3 decades definitely, even more. And HPC has applications beyond science like in climate weather prediction, manufacturing, materials, transport, geoscience, finance, in health sector. There has been countless applications of computer. Now, the question is, where do we stand when we are at this change of paradigm? As I mentioned, you can almost no way connect what classical computing is and what quantum computing is, because quantum world is entirely different from classical world. So you will have to come up with new strategies, new computational strategies, and that's where the discoveries of quantum algorithms, etc. are very much important. It's not that you have something in classical, you just translate it to quantum. It's completely new. Then the question is it a competition between the classical computer or a quantum computer? Will be someday your friend will tell, okay, now I have a quantum smartphone in my pocket and mine is better than you. That day will never come for sure. Quantum computer is never a competitor for a classical computer. But what is this? It is a complementary to technology. There are lot of roadblocks for classical computer. Even with the supercomputers, there exist many problems, real life problems, which cannot be solved in no way using a classical computer. And that is the point where quantum computer may help, and that is where the entire world is now exploring, whether quantum computer will be of help. This is of many use. Even the big giants like IBM, they are investing a lot of money in developing quantum hardware. That is expensive, but they also need to know what will be the uses of their machine, who will be their buyers. If they don't see buyers, they will definitely not build it just for fun or will not invest so much. So that is why at this point of time, it is really very important for a nation, for everyone to understand what will be the applications of quantum computer. What will it be used for? It will not be used as a replacement for your smartphone. Then why are we investing in that? And as I mentioned, quantum machine is very difficult to make, very difficult to control, very expensive. Then how can we use a combination of whatever classical computing we have, be it machine learning? Machine learning is something, AI/ML is something which has developed now, and it is of very great use for several problems. So how can you combine those classical computing outcomes with a small part of quantum computing as required to provide a most useful solution? And this gives a classical quantum symbiosis, which is sometimes referred as hybrid computing or hybrid approaches. And this is the way. You have no other way to go forward because quantum computers are difficult. So yeah, these are some of the pictures that you have seen a lot of times over internet, and if you will come to your news feeds, these are the big giants, tech giants worldwide who are investing a lot in quantum computing and preparing state-of-the-art quantum computers. We have a national quantum mission in India, which is also working in the same direction, so that we can now say, yes, we have at least entered the quantum computation era. And we have the lesson from classical computing era that computing is even beyond data science. It is an aid of discovery, aid of welfare, and it requires to be used. So the question is now is how quantum computing can be used for larger application and can be even applied for societal applications, as we have received the set of problem statements which include some of this. So, summarizing what I said, quantum hardware is very much at its infancy, but we have the understanding from classical computing era so that we are now ready to identify the applications in quantum computing and to make progress towards that. It is not something that we will achieve in a day or two. It is a long process and we are part of it. We will have to make some progress in it. So yeah, this is kind of, I have already mentioned. The first task is identifying the applications. So this hackathon gives you that opportunity. It gives you a set of problem statements which has already been identified by experts. Now it is your role how you can take it forward. So how will you have to do it? You will have to anyway map it to a language of quantum computing or a quantum mechanical system so that you can use the power of quantum mechanics to get advantage. That is what is known as quantum algorithm development. Then you will have to implement that algorithm using available hardware, be it IBM hardware or the hardware you will get in AWS. That will be facilitated at a later stage. And you will have to think of scaling. Here I mentioned one part that we identify this as our role. Who are us? Most of us, we are not really building a quantum computer. We are not doing an experiment like as IBM experimentalist researchers do. We are not building a hardware in this hackathon, but we are assuming we are given the hardware, how can we use it for applications? And this is the big visionary idea that famous physicist Richard Feynman had in 1981. He realized that more than 40 years back that our universe is quantum mechanical by nature and we don't understand most of it. So we need to find a way to use nature to understand nature. And that is where comes this the concept of quantum simulation. So what is kind of quantum simulation? Here, if you look at my slide, you will see that I have described two systems. One is a quantum system which you want to understand. And here I call something as a quantum simulator. This is a system you can think of the IBM quantum computer which will sit in Amravati is this one, which is a neural control. So you can control it, and if whatever you are measuring from here, the outcome of the experiment, you are mapping that to say something about here, where this quantum system you can think of is a very complex protein that you don't understand, which is necessary to understand for a specific drug discovery. Which there is no other way to understand that system. You map it to your available quantum system, which is like an IBM quantum computer, and you understand it. And you map that knowledge here. This is what is known as quantum simulation. You simulate a quantum system by another quantum system. And this is a very useful or most useful quantum computing approach, which shows that there will definitely be an advantage because both are quantum inherently. So there are various quantum simulation platforms. You might have heard some of the names like neutral atoms, trapped ions, superconducting qubits as the IBM one, NMR qubits, photonic qubits, blah blah. Each has their own technological stage of advancement with its bigness, strength, and usability. So those are the research part that you will have to do. You propose a solution, you will have to identify what kind of platform is more suitable for your solution. Yeah, let me skip most of this part. So this is what I call as quantum simulator. Quantum simulator is basically analog of the early days of application-specific integrated circuits, which people used to have back in 70s or before that. Then comes the modern days PC, which is like called universal quantum computer, which can do any job. This is somewhere we are approaching, but we are yet to completely approach the history or the popular ones that you will find, which uses kind of a Python circuit in emulating a quantum system. There, the strategy is mostly based on universal quantum computer. So, if you make a universal gate, that should be applicable for a wide class of systems, not very system specific. But there are also certain problems for which a specific system works in a superior manner. That researchers are continuously working and exploring. So this concept of universal quantum computer is not even new, like you will see. Is there a question? So universal quantum computers, an example of that is the IBM quantum computer. computer, although you can even use that as a simulator. Okay. So, what is your goal? As I mentioned, the whole thing starts with setting up a problem statement. And the problem statement has to be domain specific. For example, in the previous talk, we heard that a candidate problem statement comes from the agricultural domain. Right, so identify the problem statement, then you will have to choose a certain computational strategy. You can choose digital quantum computer, analog quantum computer, which are like the simulators I have been mentioning, which is particularly useful for quantum chemistry problem that you have in your ESTOP problems statements. And most of the cases, the problem statement will have to be hybrid. You will have to use HPC as well as the quantum processing unit, QPU, and then developing algorithm. Once you do that, you will have to focus on an improvement strategy. If it is just reproducing whatever you could do with classical computer, okay, it is fine. It is proving some proof of principle for quantum computer that it is capable of doing that. But quantum computation is expensive. So you may not really want to use it for some trivial problems which you can anyway solve with a calculator, like adding two numbers. You are not going to use a quantum computer to add two numbers. So you will have to focus on an improvement strategy. The problem statement, where is the limitation of high performance computing and where is the promise of using quantum technology to yield certain improvement. This hackathon, it will be most useful for you if you maybe just focus on this part. That makes things really useful and it can be pursued even in future. Then you work out these improvement strategies, work out the enhancements, and that includes optimizing resources, error mitigation, blah blah, all those techniques, and finally you deliver the unique and improved solutions to the end users. In the previous talk, as you heard, that you may be setting up a business, setting up a startup at the end of the day, and you will be delivering some solutions, maybe to the government, to your clients, but these solutions are to be achieved via these few steps. So this hackathon starts from here. This is given to you. Your job is to do enough research to understand what path you choose and what is the improvement strategy that you can focus on. So it requires a lot of research work because this whole thing is a research topic. So it's your journey in research that begins here. Yeah, so let me skip. There has been a lot of research going on in this particular area, and this number of research works is expanding a lot. So you will find a lot of resources in internet. There are too many open access papers or even the papers on archive which you can access. You should sit down with your mentors, your professors in college, and to understand which one is suitable for you and proceed from there. So for example, here I flash a set of very highly cited famous papers which focuses on quantum simulation of main body quantum systems. And what is that applied to? That's applied to discovery of new materials. Discovery of quantum chemistry algorithms lead to novel drug discoveries and even beyond. So the whole idea is how you understand how electrons behave inside the matter when they are strongly interacting with each other. Understanding that better will give you certain algorithms, and that will finally lead to quantum simulation for material discoveries. So the aim here is to do, so material discovery beyond whatever is happening right now worldwide. And the end users, of course, are material scientists, chemical engineers, and it will also lead to new science. science directions as well. Yeah, these are some of the material discoveries articles. What I personally work on is understanding fundamental particle physics. You know that whatever we see is consists of protons, neutrons, and electrons. So this nucleus, when a nucleus of a particle is focused on, that is created out of quarks and gluons. But we don't understand that fully. No one knows in the world why quarks are bound together to form a proton. That is an unsolved problem and is a Millennium Prize problem. No one knows that in these large-scale particle accelerators like LHC, the particles are moving and they are colliding with another particle, new particles are being discovered. But there is no strategy, computational strategy, which can tell you, okay, at this time, at this physical point, we will get this particle. So these predictions, which are absolutely important for all these large-scale sophisticated experiments, the tool for this prediction is absent even using largest supercomputers. So that is why the particle physics community, high energy physics community is solely relying on quantum computer to give that answer. And this is a very interesting idea that this computational research for particle physics was co-developed along with the hardware development of supercomputers. It started in late 70s and even the early IBM computers were named after this QCD process as their processors. So this is a journey of co-developing science and co-developing computer architecture. I mentioned of Feynman. Feynman was a very much enthusiast of quantum architecture, and that connects these two communities closely. And right now, there are these unsolved problems which even these biggest supercomputers present in all the national labs in the US can't answer. So the question is whether quantum computer will be able to give the answer. So there has been a lot of research over the last 10-12 years in these directions, and you will see plenty of papers in the archive and all, but still we are not very close to the final answer yet, and the journey continues. In my research group in our department, we are also seeking answer to one of such very big problems in the world. And we are also collaborating with worldwide researchers in this problem. Okay, so I will not go into details of that, but to summarize, quantum computing applications exist beyond scientific problems, such as there are applications which has been studied in great deal in finance. So tomorrow you will have a presentation from finance sector, I think, from Q Krishi. Rishikesh will be presenting how quantum algorithms can yield better finance solutions, which is of utmost interest to banking companies and finance organizations, fintech industry as such. So there are various problems, and that has been studied. Even this is a roadmap paper written by from Q Krishi as well, who will be presenting tomorrow and will give more detail of that. How quantum computing in finance is a very important, and one should focus on this use case seriously. I think there is a problem with that as well. If any of you have heard of solving Navier-Stokes equation or the understanding fluid dynamics problems, many of you, when you travel by air, you often face turbulence. And aircraft designing has to deal with that how they actually deal with turbulence. So this understanding turbulence is an unsolved problem in nature. It is also another $1 million problem. So this $1 million Millennium Prize problems are all big candidates of quantum computing, because it's a new technology and the aim is whether one can use these new technologies to give you answers. So quantum computing for fluid dynamic systems is of very much importance, but yet it is very little developed so far. So we are also starting to work on this. Many leading researchers worldwide is working on this. This is just a very big problem to think about. And not only that, there are even industries, for example, this is IBM and this is a Tel Aviv-based startup, Classic, who are investing a lot in understanding performing quantum fluid dynamics. And there has been a lot of research work that is happening. Every day new papers are coming, roadmaps are being set to these new research directions. I'm not sure if there is a problem on computational fluid dynamics in this boot camp, but this is a very big problem to look for you in the future if you find it interesting. What you heard here more common is machine learning and something called quantum machine learning. So here at this point I must make you cautious that quantum machine learning is a kind of a metaphor. You should not use the word often. Rather, you can try to combine machine learning and quantum computing to provide you certain answers. Because machine learning always deals with a large number of data. And handling a large number of data leads to handling with a very large quantum systems and their complicated operations, which makes a lot of error in the data. So there is no proven way of maintaining a data set on a quantum computer or accessing a large data set on a quantum computer. So large data is not the natural thing to do used on quantum computer. For that you have machine learning. But then there comes certain quantum inspired machine learning algorithms which utilizes some certain features of quantum systems to give an improved machine learning solutions. That is often used best. And there has been a lot of work going on in that direction as well, which you can also explore while coming up with your strategy for attacking the problem state. Yeah. So to summarize whole thing, quantum computing is kind of an ecosystem. Quantum computers are capable of doing certain specific jobs, what I didn't cover at all, but it is also included in your set of problem statements, is quantum communication or cryptography, quantum cryptography related problems. And that is something government is very much aware of because they want to make all our data, all our banking sector quantum secure. So quantum cryptography is a very big application which one must achieve in near future. And quantum computing can be used as a tool to understand whatever is still unsolved in nature and to answer the very big questions in science. Who are interested in quantum computing? For example, people like me from academia, we are interested from fundamental knowledge perspective. There is a lot of industry people who are interested to get advanced quantum solutions. For example, as I mentioned, finance, drug discovery, agriculture, and combining AI, ML. Most importantly, the quantum hardware developers, they are also interested to know what will be the outcome of this quantum system, outcome of developing these complicated quantum computers. So, to build this complete ecosystem, of course, we need to overcome certain expertise gap when it comes to quantum. So right now we were doing your BTech degree, maybe some of you are doing MTech in college. You are learning various other topics. So this is the time for you to at least think how your problem will be connected to certain quantum computing applications or may actually gain from quantum computing. Because it may not be the case that each and every one of you will be doing a quantum computing, hardcore quantum computing in future, but still you can contribute to the ecosystem as a domain expert, as a collaborator with the quantum scientists to make the translation. How your problem of interest is mapped to a quantum mechanical system which can be implemented on a quantum hardware. So for that, I think a lot of work is going country right now. A lot of interdisciplinary conversation, discussion, training program, academia industry partnerships, designing programs like minor degrees, MTech degrees, and also BTech degrees in quantum science and technology is happening. And you are all here to participate and enjoy this Amravati Quantum Valley Hackathon, which I feel is a very important event for world. So you are aware of what are the objectives of this hackathon. Just I want to mention something that this is being a hackathon. This is a fast-paced platform. You will have to deliver within certain time limit. But this also the topic is a bit difficult. So practically speaking, delivering something by next 2 weeks, it would bring you a Nobel Prize. But that is too high for us to imagine that we will be achieving that. So rather, what the focus should be that you are learning something. So you are building something, you are learning something, and you are sharing the knowledge. A team from your college will participate in this hackathon, may go back and tell other students in the college, then say this is the excitement I felt, and you may also find this exciting, you may join. As Dr. Anil Kumar mentioned that having a quantum valley would require to have a huge workforce. So the workforce needs to be aware of what quantum at all is. So the purpose of this hackathon is to learn, to share knowledge, focus on innovation. As I mentioned, it is not something traditional. You will have to come up with drastically different ideas. So you start with a very simple theme that you have control with, and you document your journey, how you are thinking of making even a tiny advancement to this. What you think can be useful. Maybe it is not implementable right away, but maybe after 5 years it can be implemented. So document your ideas, start doing research on this topic, and of course think what you want to achieve. Not like I know this tool, I know Python, or I know C++, I know Fortran, and I will start coding. That is the second part. Rather, the first part is what is the problem that you want to do, and for that what you need to learn. You should be ready to learn many different new things in this course of action. Okay, so with that, yeah, these are the set of problem statements. It is available with you. Please go through it. Search over internet on each topic to understand which one you can actually address, you can proceed with, and then take the decision, make your problem statement, make your proposal slide. Okay, with that, I will just say that this hackathon is less of a winning, but about beginning, connecting, and collaborating for the future of technology.